Now, magnetism lesson 9. In magnetism lesson 8, let me show you once more and then proceed with lesson 9. In previous lesson, magnetism 9, we derived this expression. There was a loop carrying current, let's say anti-clockwise when seen from the top, and when seen from the bottom it is clockwise. So the top was behaving as the north pole of a magnet, and the bottom was behaving as a south pole. Means this loop carrying current was behaving as a magnetic dipole, means a south pole and north pole. So means lines of force due to this loop carrying current were entering from the bottom and leaving the top. So it was behaving as a Bohr magnet, right? Now, and we derived its magnetic moment in the last lesson was I times the area of this loop. That is what we derived in the previous lesson. Now let us go to a new one, magnetism 9. How atom as a magnetic dipole. How atom behaves as a magnetic dipole. If it behaves as a magnetic dipole, and a magnetic dipole has a magnetic moment, that was M was equal to pole strength times 2L for a Bohr magnet. And here we will see how the atom behaves as a magnetic dipole and what is the relationship between magnetic moment and the angular momentum. So let us proceed. This is the derivation and it is important also for your board examination. We know for a Bohr magnetic moment was the pole strength times the length of the magnet. The length was this length 2L, was from south to north or from north to south, that is magnetic length. And this was M was directed from south to north, it was a vector quantity. And for a current loop in magnetism lesson 8, for a current loop, we also derived this. M was equal to current times area of the loop. Where M is the magnetic dipole moment pointing from south to north, that we have discussed time and again. Now look at this diagram and then proceed. This central portion is positive, that is the nucleus, and as you know, nucleus is positively charged because it has fundamental particles like proton. Proton is positively charged, neutrons are neutral, so as a whole it is positively charged. Suppose an electron is moving like this, ME. Here it is written M with a subscript E, means mass of the electron. It is moving in a circular path, and we know when something moves in a circular path at any point on the path, the instantaneous velocity is along the tangent. So V is the velocity of the electron. From the center to this point is the radius of the circular path. And L stands for angular momentum. And we'll see how this angular momentum is pointing this way if the electron is moving anticlockwise. If it is moving clockwise, this angular momentum will be pointing vertically downward. Okay? And we'll find out relationship between angular momentum and the magnetic dipole moment. Now, let plus the positive nucleus of the atom, this one, ME, mass of the electron, V, its speed in the circular path. Because the direction is continuously changing, so I have not written V. At this instant, the velocity is to this side. This is the magnitude of the velocity, moving at constant speed, right, in a circular path. R is the radius of the circular path, and we know from your kinematics, linear momentum is mass into velocity. Since I have taken the symbol M with a subscript E as the mass of the electron, therefore linear momentum will be mass into its velocity. At this point, what will be the direction of the linear momentum? To this side. At this point, it will be along the tangent. At this point it will be along the tangent. At this point it will be along the tangent. It is a vector quantity. So the linear momentum. Angular momentum will be momentum, the magnitude of the angular momentum times the perpendicular distance from the axis of rotation. Since L is equal to r cross p. Remember, angular momentum is r cross p, where p is linear momentum. It is not p cross r. If you take it p cross r, the magnitude will be same, the direction will be different. So you have to be very careful regarding this line. Angular momentum is r cross p. What is the direction of the angular momentum? Is same thing as the direction of r cross p. Now let capital T is the time taken by the electron to go around the circular path once. This electron to move around this circular path, let the time taken is capital T. Means in T time it makes one revolution. Means it passes any point on the orbit 1 by T times in 1 second. This is important to understand. This is in T time it is going once around it. Means if you start from here, if you start counting the time from this point, then to travel from this point along this path and come back to the same point will be time t. If you start from this point, starting from here, going along the circular path to arrive at this point, it will require the same time because the speed is constant. So it passes any point on the orbit 1 by t times in 1 second. Means this is the frequency. So the current, as we know, current is equal to charge over time. I is equal to Q by T. So I is equal to E. This can be written as E by T, where E is the charge of the electron. E by the time is equal to your current. So E is equal to 1 over T. Now, then come back here. Now, since the path is circular, this is the circular path along which it is going. So radius is r. So this distance, the circumference is 2 pi r, and the speed is v. So distance by speed is your time. So v into t is same thing as distance. So now substitute this value of t in the expression for current. I is equal to charge of the electron 1 by t. For t I put this thing, so v comes to the numerator, so it becomes ev over 2 pi r. So when that electron is taking time t to complete one revolution, the current associated I is equal to ev over 2 pi r. Charge of the electron, its speed divided by the total path traveled, that is 2 pi r. Make it equation 2. Now, we know magnetic dipole moment of an atom. This is what we had derived in the previous lesson. So, if this radius is r, the area will be pi r square, and current we have derived, and this we had derived in the previous lesson. So your magnetic moment will be I ev over 2 pi r, area of the circular path, that is pi r square. So pi cancel, 1 r cancels. So ev r over 2. This is your magnetic moment. Now, we know angular momentum is equal to momentum times the perpendicular distance from the axis of rotation. Now, linear momentum P is equal to mv. There is one angular momentum. The equivalent of mass in rotational motion is I. The equivalent of v in rotational motion is omega. This is one type of expression. There is another expression also. L is equal to O, the momentum times the perpendicular distance, that is r. So m comes to this side, mass of the electron. So we are left with Vr. Means here for Vr, I can substitute angular momentum by mass of electron. So So this expression reduces to this expression m, which is EVR over 2, reduces to E by 2, E by 2, E by 2 VR. For VR, I substitute L by ME. L by ME. So I keep this mass of the electron along with 2 because this is a constant, this is a constant, charge of the electron is constant. So some constant into angular momentum. So your magnetic dipole moment M is equal to E over 2 times mass of the electron times the angular momentum. I have put a negative sign because the charge of electron is negative, where E is the charge of the electron, that is 1.6 into 10 to the power minus 19 coulomb. There is no need to remember this value because in numericals, when numericals asked in JEE examination, you are not required to remember these values actually, because the numericals are set in such a way you get a good figure, everything gets cancelled. So let us go to the next page. Therefore, so what is the meaning of this negative sign? What is the meaning of this constant L M is equal to minus this constant into L? Means whatever will be the direction of M, that will be negative of the direction of L. Means M is opposite to the direction of L, angular momentum. That is what I am explaining here. So, therefore, M and L, magnetic moment, angular momentum, are opposite in direction. That is the meaning of the negative sign. Now, this is important. Bohr's theory. This you must have done in chemistry also. The angular momentum should be integral multiple over h over 2 pi, where h is Planck's constant and integer. N can be 1, n can be 2, n can be 3. This is what we did in chemistry. You must have done in chemistry. So, your M, which I just derived as E over 2 times mass of the electron and times the angular momentum. The negative sign only indicates the direction, but the magnitude of M is equal to E over 2 times mass of the electron into L. And for L, I can substitute this Bohr's quantization. So, NH over 2 pi. So now this becomes 2 into 2, 4, pi, mass of the electron, in the numerator, NEH. So, this is the magnetic moment of an electron due to its orbital motion. And we just explained M and L, capital M, magnetic moment and angular momentum, they are opposite in direction. Now for n is equal to 1, here the minimum value of n is 1. So if you put n is equal to 1 here, for n is equal to 1, your magnetic moment becomes EH over 4 pi ME. E has a standard value charge of electron, that is 1.6 10 to the power minus 19 coulomb. H is Planck's constant, that is 6.62. 62 के आगे में और भी digits है, into 10 to the power minus 34 joules per second divided by 4 pi value you know is nearly 22 by 7. Mass of electron 9.1 10 to the power minus 31 kg. If you solve this in a calculator, scientific calculator, you get it as 9.27 10 to the power minus 24. And what will be the unit? We had earlier derived M was equal to I times area. Ampere, area is equal to meter square. Ampere, meter square. This is called Bohr Magneton. That is the minimum magnetic moment possessed by an electron. So that is all about. Then we will slowly move on to Earth's magnetism. I'll do it tomorrow for you. Okay. So if this figure was not clear to you, let me enlarge it so can, of course, while you are watching in YouTube, you can enlarge it, but still let me do it for once for you so that it is visible to you. Oh, right. I think it is visible now. Okay. Thank you.